Okay, so I had a request to go over the equations for this chapter, those dealing with Newton's laws, forces, and friction, but I don't want to go and give you all of the equations at once because that could be a little bit overwhelming. Now, we're not going to talk about friction for probably another week. We're just going to keep it in general sense here, just dealing with forces, finding equilibrium forces, net forces, things like that. So for now, I'm just going to go over the general equations. So to start off with, we have probably the second most famous equation in physics behind E equals mc squared, and that's F equals ma. So that would be this equation here. Now I wrote F net equals ma because that's really what's going on. It's not just a generic F equals ma, but F net. So it's the net force. So it's the mass times acceleration, and as an object's mass would increase, right, the amount of force to achieve the same kind of acceleration would have to increase as well, and it would increase proportionally. Now, if you were to increase the mass of the object but maintain the same amount of force, you're going to notice that the acceleration is going to drop. We know that if we start to push something that's heavier with the same amount of force as something that's lighter, the lighter object is going to accelerate faster, the smaller object is going to accelerate slower. So there's a direct relationship with the mass, and there's an inverse relationship dealing with the acceleration. Now, another way to rewrite that is just sigma F equals ma. Now, sigma means the sum of whatever is following it. So like delta means the change in whatever, change in x, change in y, change in time. Sigma means the sum of what's after. In this unit, we're talking about forces, so it means the sum of the forces, and therefore net force. So the equation below that one is the F net x and F net y's can be rewritten with sigmas, and that just means the sum of all of the x components and the sum of all of the y components. Now those are added together. What you have to consider is the directionality. Since force is a vector, it has a direction to it. It has a positive and negative, it has an angle, all of that. So if we look at the example on the right-hand side, the F1x is going to be in the positive x direction. The F2x is going to be in the negative. So when you find the net x value, you're going to take F1x and subtract F2x. Now, if you're going to go do the y values now, so finding F net y, both y's act up in the positive y direction. So you're just going to add those things together. Don't worry about subtracting anything. The fifth equation down, F net squared equals F net x squared plus F net y squared. That is the Pythagorean theorem with the components of your net force. So after you find the F net x and the F net y, you generate a triangle with the net force components and the total net force. So that's going to be the bottom right. So at the bottom right here, we have F net x drawn in blue, F net y in red, F net total in green. That is a right triangle. So we can do the Pythagorean theorem, like I said, take F net x squared and F net y squared, add them together, take the square root, that gets you F net total. So that gets you the magnitude of the net force. Now, net force, scalar, is a vector value, so we need to also have a direction to it. So that's where the theta comes in. So theta equals inverse tangent of opposite over adjacent. You could use cosine or sine, it's up to you, because at that point in time, you probably already have the total net force. So any of the trig functions are viable. I tend to always go to tangent because I've already solved for x and y, and that's just kind of my thing. All right, but it's up to you how you want to do it. Now, in this case, I just left it opposite over adjacent because depending on the orientation, x and y may change what they are. So looking at the top example, in the case of F1, opposite is y, adjacent is x. And F2, opposite is x, adjacent is y. So when you come down here and you're finding the angle for net force, pay attention to where your theta is going to be. In this case, opposite's y, adjacent's x. If we had theta measured off of the y-axis, that would flip. Okay? Now just a brief explanation just to remind you here. This top right one, I drew the triangle for the force values with their components with two different ways theta can be written. I have theta written off the x-axis, theta written off the y-axis. That's just to remind you and show you that if it's off the x-axis, that means y is going to be opposite. It's going to be sine. X is adjacent. It's going to be cosine. If theta is off the y-axis, it flips. X is now sine. Y is cosine. Another thing you can keep in track of, just to make sure the values make sense to you, is your relationship between theta and your components. So if theta is greater than or let's start with theta is equal to 45. So if theta equals 45 degrees, you would get that your x component would equal your y component, right? Now, if theta were less than 45 degrees, that is going to be x greater than y. And if theta were greater than 45, then you would have y greater than x. Okay. Now, these things flip based on where theta is, because this whole setup here, this is all based off of the theta off of the x-axis. Okay. If you were to have theta measured off the y, those values would flip around. Okay. And that's it. Okay. So one of my suggestions, if you're not comfortable with making sure that you flip x and y, whether it's sine or cosine, is once you get an angle that's measured off the y-axis, just go ahead and use the angle off of the x instead. So in the case of this one, I would say this is probably somewhere around 55, 60 degrees. So instead of using theta 55 or 60, I may use theta of 30, 35 down here, and then I can use my x off of the x-axis, my y off of the y, and use sine and cosine like I did over here. Sine for y, cosine for x. And that's basically a summary of the general equations we're going to start off with. As stated earlier, friction stuff you'll get sometime next week. If you have any questions, email or stop by during my office hours. Have a good one.